Okay, this is a talk about stable isotopes enrichments, which is maybe one of the better kept secrets at this facility. It's totally unclassified, but overshadowed by a lot of the space and nuclear things that we've done, which certainly are important in that. But this is an interesting collection of scientists that looked at a different problem of how do you enrich the various isotopes of stable gases, non-radioactive gases. And we're going to tell you that saga tonight. With me, I've got Frank Smar, who is still working on separating isotopes at Cambridge Isotopes Laboratory. But he was on the HH staff, and we'll hear about some of the work that he did on chemical exchange, etc. We also have Bill Roos, who had another engagement that competed with tonight, but he's provided a lot of the information that will be presented here. So this is our team of three, and we're delighted to have a number of the HH workers here amongst us, and we'll see you as time goes on. The outline of this talk is, first of all, the assignment itself. It came in 1954. And we're going to talk about the isotopes that were enriched, their end uses, and who was doing the work. The science and research behind separation methods will be discussed, and we'll talk about a number of isotope enrichment methods: gaseous thermal diffusion, liquid thermal diffusion, chemical exchange enrichment, and displacement band chromatography. We'll also talk about the many contributions of the stable isotopes group, or the people therein, contributed to other things in nuclear and in the space program and elsewhere at Mound. And then we'll talk about the enrichment production sales. Yes, we were a busy business and selling product, which led ultimately to commercialization. So that's the outline of what we're going to talk about tonight. Mound received the stable isotope enrichment assignment from the AEC in 1954. This was pretty welcome because in 1953 there had been a layoff, and so there was a real drop in the employment here at Mound. So the idea of a new program coming in and staffing up for it was certainly welcome. Oak Ridge was to continue to enrich metal isotopes using the tools they have available, like calutrons, which are big magnetic mass spectrometer separators that one atom at a time you separate the metals into different buckets. And they also, of course, did enrichment of uranium by other means also. But Mound was to focus on enriching gaseous species. So the isotope separation began by the first thermal diffusion column, which was in our building, not down in HH. And it was done in the late 50s as they were just getting up and running as to how do you separate these isotopes. There's some literature out there, but basically this was kind of an invent as you go. When the polonium production work ended in T building, the building just below them, called the hydrolysis house, better known as HH building, that was available. It had been used to process the effluent from polonium extraction and dissolution of the bismuth slugs and that. So there was a lot of chemistry that went on to neutralize acids, etc. But this building vacated when polonium left as a program, and so it became available later to form the complex that's shown on the side here of office areas and then the labs themselves and a stack. That's pretty touchy. Okay. So the experimental isotope separation then started in HH. just to give you a snapshot of how the organization was working and the extent of it, this is a snapshot of a org chart in 1971. And the head of it was Walt Habaugh, who reported to Bill Cave and Ralph Newberg. There were 4 major groups that Habaugh had: the gas dynamics and cryogenics group with Bill Taylor leading that. We're going to have fun. The separations research group that was led by Roger Schwind, with a number of people under that, many that continued for many, many years. And then there was the stable isotope sales group over here. Lumped together with them were the radioisotope separation people with names that you recognize. Sitting in the audience is Paul Figgins and Dick Matting. So that was part of Habaugh's group at this time. So that's just a snapshot of the organizations, the 3 separate organizations of gas dynamics, separations, and isotope sales.
Just to interrupt for 1 second here, you're going to see a lot of names, and we probably forgot some people. There may have been close to 100 people that passed through the organization and made significant contributions over the years. I keep thinking of them, but there's only so many things you can do to change slides up until the last minute. So if we forgot you, sorry. We're all getting a little bit older, I guess. Don't remember everything. So
might be a good time to acknowledge at least 2 that we met that are here tonight, and that's Mary Sizemore and Bill Saul, who we'll find out later did work on the mass specs to analyze their products. Okay, so what are isotopes? Let's just get the basics down. Isotopes are atoms of an element with different number of neutrons in their nucleus. So they basically add atomic mass to the nucleus. Chemically, they're the same as the defined by the number of protons. So some examples. So let's look at the simplest one, which is hydrogen. If you have 1 proton and an electron around it, that's called hydrogen, and we know and see that often. The next one is if you add a neutron to the nucleus, you make deuterium, which is heavy hydrogen, but heavier yet is 2 neutrons added to 1 proton, which is tritium. But by adding that extra neutron, you now have a system that is not stable for the long term. It's not a stable isotope of hydrogen. It's a radioactive isotope. And what happens is the neutron kicks out an electron and becomes a proton, and it becomes helium. But in the process, you get some energy off from the tritium. Okay, another example of that is carbon. Carbon has 6 protons, and that's true of all of its isotopes. It has 6 neutrons for carbon-12, 7 for carbon-13, and 8 for carbon-14. You might recall that carbon-14 is used for carbon dating of things, and it actually is radioactive. And so as time goes on, it can disappear. There's an expectation of how much should be there, and if you can measure how much is depleted, you can come up with an age for that particular item. It stopped taking on carbon when it died. Higher masses typically have more isotopes. So what are they used for? Some of the uses of stable isotopes is the fairly obvious one of compound labeling, where you can attach an isotope to a chemical compound that you're trying to fabricate, and you can measure what happens when I put it at different places. And from that, you can infer what's the structure of this new chemical that you have made. So that's a common use of carbon-13, and in some cases, deuterium labeling is done also. The carbon-13 is NMR active, so you can actually see a signal from where it is in this thing, and so there's plenty of ways of using it for diagnostics. Carbon-13 makes labeled carbohydrates to be ingested to study metabolism, because ultimately your body absorbs these carbohydrates and turns them into carbon dioxide, which we expel each time we breathe. And by looking at a person's breath, for someone that's ingested some carbon-13, you can look at the mass 45 peak, which is carbon-13 O2, and see it being higher than natural abundant value. And by monitoring that, and you can see what is it as a function of time, you can plot out the metabolism rate of the patient. Another one is reactor fuel labeling that was done using unique xenon isotopes, enriched krypton isotopes, added as a mixture to the cover of the stainless steel fuel pin that was made. Bill Roos worked a lot on this with the Hanford reactor folks as a way of labeling fuel pin. The idea was you put the fuel pin in the reactor and a year later it ruptures due to too much gas buildup inside or whatever, and you can look at the cover gas, which already has both krypton and xenon in it, and you can look for the odd isotope that sticks up. And from the combination of the odd xenon and odd krypton, you can figure out which fuel pin was ruptured. As you might imagine, it got a little complicated pretty quickly. So, to the best of our knowledge, it's not used now, but it is in fact an experiment that was tried and it worked. Another more common use of oxygen-16 is right here with our space program. Plutonium oxide was the fuel form that was used for the RTGs, but it wasn't an ordinary oxygen. It was oxygen-16 that was done, and this was used to avoid the oxygen-18 and having a reaction with the alpha emitted by the plutonium-238. That would give rise to a neutron, and the neutron would go out and maybe hit the electronics of the spacecraft, and the whole mission might die early. Therefore, it's worth making oxygen-16 as the oxygen used in that fuel form. Oxygen-17 and 15 are part of easily traceable in the soil if you give it as part of nutrients like nitrogen compounds and so forth. Xenon-129 recently has been used to look at respiration in the lungs just by using the magnetic property of Xenon-129's nucleus. You can actually see a respiration and blood flow using magnetic resonance imaging, and that's recent since Mound is down, but it's a product for Frank.
Yep.
Okay, so another use is pure isotopes for fundamental physics. For example, the group in HH enriched argon-40 to 99.9968% argon-40 so that there would be a single isotope in which to put inside of a cavity resonator. Then they would measure the speed of sound. As long as there's only one isotope of the gas, namely argon-40, you could get a value for the universal gas constant that is better than anything done previously. So Mound made the gas, we shipped it to them, they used it, they published the paper, and I'm not sure we were cited, but you know, that's how it goes. We have carbon-13 enriched to 99%, used in a variety of applications that we'll talk about later here. The key thing about, if you look at this list, all of these are users that we normally call customers. So this is where you would send it. One more quick one that's just too interesting to not talk about. Carbon-13 labeled urea capsule can be used to detect H. pylori bacteria as a source of a digestive problem. If anybody has had ulcers, one of the indicators for that can be the presence of H. pylori bacteria in your body. How do you measure it? Well, you ingest this carbon-13 urea capsule, and the bacteria take the urea and digest it, and it ultimately ends up as carbon dioxide, which we exhale. So you give the pill to the patient, and some short time passes, and then they start taking samples of your breath by breathing into a bag. And then by analyzing the samples, if an unusual amount of carbon-13 shows up above the natural abundance, then there's some possibility that you have this H. pylori, and you can begin treatment for that for your ulcer.
And to interject one more thing, this is a major use worldwide. Not so much in the U.S. But we make this now in our facility in Xenia, Ohio, and we're one of the top producers in the world, if not the top. But most of our stuff goes overseas, to Asia especially, and to Europe. The other thing about the H. pylori test is that it is also implicated in certain kinds of heart disease. So there's some diagnosis of H. pylori with the breath test, but that might indicate you've got it in other parts of your body. They start looking for infections or whatever that cause heart trouble. And in the end, this is one application, started at the Mound with like a column hanging on the side of HH building, and then it grew up later at Los Alamos because they have the natural advantage of being able to dig a deep well in the sand. But this is one thing that went totally commercial and has been a huge success from this program.
Another one is you can make radioisotopes out of the stable isotopes. So there are many short-lived isotopes, medical isotopes that are used for diagnostics. One is fluorine-18, which is a positron emitter used in the positron emission tomography, better known as a PET scan. Basically, they're looking for rapidly growing cells, which we normally call cancer. And so with these scans, you can spot areas where the PET scan has indications, can indicate that cancer has spread to that particular area. So how does it work? Basically, we use oxygen-18. Again, a major supplier is here in Xenia. Oxygen-18 is a target for protons right in the hospital. You can hit oxygen-18 with an 11 MeV proton, and you make fluorine-18. Then that fluorine can be attached to a sugar carbohydrate and given to the patient. So the sugar is taken up into the bloodstream, and it's also taken up very rapidly by rapidly growing cells. And then wherever those cells has taken that fluorine, when the fluorine decays by positive beta emission, positron, it finds another electron within a micron or so, and what you have is annihilation. That the positron and the electron literally annihilate and come off as two gamma rays in opposite directions. So that not a single one, but two of them, so that you can conserve momentum. But they are about a half an MeV gamma ray, which is easily seen by imaging techniques for other kinds of imaging at the hospitals. So they look for those, and from that you can image where did the positron emission come from in the body. Another one is xenon-124, enriched at Mound to maybe 70 plus, I think you said 90% was probably the highest we had here.
Near the end, we were making 124 and 126 at over 99% using some advanced thermal diffusion technology, as well as a pre-enriched feed from the centrifuges at Oak Ridge. So we got this up pretty good, and it's been fair in terms of a research project that has not gone clinical. The 018 is clinical, and we sell, I wouldn't say tons, but hundreds of kgs of the stuff in the US and worldwide. And if you get a PET scan for either cancer or even like MRI 3D images for other parts of your body that are not cancerous, it's fairly likely that you've got 2 or 3 suppliers in the world to pick from, and we're one of them. So, and it's all developed here from our sales effort for material that was mostly coming from Oak Ridge, or I'm sorry, mostly coming from Los Alamos for the oxygen 18 part.
So the big benefactor for this isotope enrichment is the nuclear medicine. They are a prime user, and we're glad they can. Helium III was an early Mound product and remained a top seller. We'll see later some of the sales statistics. Helium III is a decay product of tritium. It has a 12.36-year half-life. And wherever you store tritium, you have Helium III accumulating. So the tritium is made in a reactor with a lithium neutron reaction. But the purification of Helium-3 was done receiving bulk amounts of Helium-3 that had a little bit of tritium in it. But what they did was to purify it and remove the tritium contamination such that they could sell it as a non-radioactive gas. And where was this gas used? It was used for a lot of scientific research. Helium-3 is a very interesting nucleus to work with. And it also has a high neutron cross-section. So you can put it into a gas-filled neutron detector as a principal way of detecting neutrons. For example, if you're looking for neutrons at the portal of for ships to go through, or a portal at customs, these neutron detectors can see if you have something that is emitting small quantities of neutrons. Recently, there's been a shortage of availability of Helium-3. We can't solve that right now.
That all went back home to Oak Ridge and Savannah River when the Mound shut down. We had a bloody ton of the stuff that could have made you millionaires, but they basically shut the program down and reapportioned all of the Helium-3 that was cleaned up and sitting there back to Savannah River and Oak Ridge for whatever purposes they use it for. One of the purposes might be they can make tritium again out of it if they had to. So.
Okay, switching gears now, we're going to look at the Bill Kaler's group and the fundamental physics of molecular collisions that was done. He basically had a very large chamber. The pictures on the right here show the size of a chamber, and you can see from the individuals like Bill Taylor on the right and a visitor from France on the left. These are large chambers. I mean, probably doors on them like that. The idea is that you can put one isotope into an oven that will make a molecular beam effuse out, and you can focus the beam, or at least channel it with apertures, so that it appears at this point, and you can have a different isotope go in the direction 90 degrees from it, and then you can look with a detector at the scattered results of that. From that, what you get are the shape of a particular potential well that can be inferred from the scattering data. Now, that's about as fundamental basic physics as you get, certainly at Mound and probably anywhere. And there were a number of theses that came up with a unique scattering potential for some of the people. From this one, diffusion parameters actually can be calculated using the shape of that particular well to estimate what would be the separation factor induced by collisions and thermal diffusion. So this is the basic information that can be used. The gas dynamics group also determined the thermal diffusion coefficients for gases of interest using a Trennschakel device. So, was bedeutet Trennschakel? Trennschakel is basically a swing separator. If you look at this little design on the left, this is a piston that goes up and down, and it takes a single quantity of gas, pushes it down in this direction, and then as you go to the center point, it pulls back and pushes the gas in the opposite direction. So what does that accomplish? Well, it makes the gas exposed to a hot region and a cold region. And after many, many, many cycles, you can analyze the composition in the hot region and the cold region, and from that you can get kind of an equilibrium separation factor for a thermal diffusion column that would operate at that particular temperature and reference temperature. So this is just the diagram of how it works, but the device that they used here was 2 bulbs, one hot, one cold, with 20 tubes interconnected in series in order to make a very long path for the gas, and that you could accomplish some good separation. That then becomes the starting data for designing an isotope separator using thermal diffusion. So this was theoretical work that came out that was used by the people that actually built the separation columns. The gas dynamics group also did research on cryogenic liquids, for example, Helium III, Helium IV, as well as distilled hydrogen isotopes, which were certainly of interest to the weapons area of Mound. Terry McConville investigated Helium III, Helium IV mixtures at the liquid temperature of Helium IV, which is 4.2 Kelvin, and then lowered the temperature of the gas down to the 2.17 degree Kelvin mark, at which time all of the Helium IV atoms say we are one, and we start moving together and experience superfluid properties, amongst which is zero viscosity of a fluid moving within itself. So you can set up convection currents and other kinds of things. The presence of Helium III, it doesn't enjoy superfluidity at all. So it, depending on the amount that is there, it can interrupt the superfluid behavior. What is this all about? Thank you. Bill Wilkes did a lot of work on cryogenic distillation of hydrogen isotopes in the range from about 14 Kelvin to 21 Kelvin. For the different isotopes, that's kind of the range at which they make liquid hydrogen. And that's a good way to store it. So the designs for the cryogenic enrichment system for deuterium and tritium fuel was of interest for the Princeton Plasma Physics tokamak. Mound was directly involved with that, and he was involved with the cleanup system in which you burn the fuel, and then later you try to re-enrich it so you can make another batch to burn. And so he did those for that particular project. But as a result, he also worked with the Mound Component Evaluation Group to enrich tritium for cryogenic distillation in other areas at Mound. We had major quantities of Helium III and certainly Helium IV and all the HDT species. So we were uniquely capable of doing this kind of research, which we did. So, separations and enrichment of stable isotopes. This goes back to the late 50s. We began with the neon, the noble gases, and later added thermal diffusion for everything that's listed here. So, who were those involved in these isotope separations? Well, we saw the Habaugh group early on. After that, a little later, there were people like Dick Valley, Roger Swin, Charlie Eck, Vince Savona, Al Rui, Joanne Gridley, and Kathy Flater. They were all part of the actual isotope sales group and the management. The next level is Bill Roos and the people that actually did the thermal diffusion enrichment of things like xenon or krypton. And with that is Dave Jones, who's sitting. Dave, raise your hand. There he is. And Bill Deal, who wanted to come tonight, but he said he has back problems, so he wasn't there. Bill Eckenroth, Gil Stuber, Don Schneider, Jerry Liner, Rondell Hurd, Marv Osborne, Mary Boyce.
Now Sizemore.
And Mary Sizemore.
No, that is me. That was my maiden name.
Oh. Oh, thank you. I thought we had totally forgotten you. So, no, very good. So now you know the answer to that. We'll put in parentheses Boyce and Sizemore. Okay, then the next group are the chemistry separation people, like Bernie Jepson, Frank Smar, who's here, Ed Michaels, Dan Grove, Leo Parts, Wu Park, Dave Jones again. Dick Epley and Bill Saul were involved in some of these projects too, to be able to do the gas analysis part. For years, the only reason I'm up here is we used to analyze all of the gases that were separated. We would give them daily information about how are the columns doing. That got a little old by the late 70s and early 80s. And so Dick Epley and Bill Saul actually computerized a mass spectrometer so that you could do the analyses locally without having to trudge up the hill. And the only problem is the guys didn't get to see the gals do the mass spec analysis. Other than that, it was a definite improvement. We, however, did continue to analyze all product that went out the door just to have a semblance of separation that, if someone's going to argue with something, it's easier for us to defend it for them. So we did that. Then the other group that is here is, we'll see a lot about Bill Rutherford. And his chief sidekick was Lane Myers, who's here. Lane, raise your hand. There he is. Okay.
Well, Tomasowski's here too. He's right behind me.
Is he? Wow. Good to see you. Well, you're definitely listed here too. Thanks for being here. This is great. And so then in the last group is Bill Taylor and some of his graduate students that got their PhDs doing work here at Mound is David King and John Hurley. And some of the senior techs were like Pat Pickett, Bill and Dr. Wilkes and McConville, but there are a lot of summer students. And I've had the pleasure of meeting some of the summer students that, after they finished their degree, they said, the summer I spent at Mound was probably the most fun I've ever had. So it was a very good program that Bill Taylor and others led to train people in basic physics. John Hurley, for example, is now at NIST in Washington. Okay, the engineered process to separate isotopes depends on the chemical form. First of all, gaseous thermal diffusion applies to noble gases and other kinds of gases like that. There is also liquid thermal diffusion, chemical exchange for metal isotope enrichment, chromatographic column separations, and cryogenic separations. And we'll take a look at each of these methods. The practical designs of thermal diffusion columns were done by the designs of Bill Rutherford. He built prototypes and tested experimentally to find optimum operating conditions. A number of unclassified general literature papers came out of this. One of them that is really important is the separation of xenon isotopes in the thermal diffusion column by Bill Roos and Bill Rutherford. So you have not only the theory behind how the separation works, you have the experimental data of separating xenon isotopes from Bill Roos. Other papers similarly on neon, argon, krypton enrichments by Bill Rutherford, and some theoretical diffusion factors actually computed by Bill Taylor and his group, and Stan Weissman, who was from the University of Cincinnati and was an adjunct employee here to work with Bill. The theory was put into practice by our chemical engineers, and they produced enriched isotopes. In doing various things, we're going to look at an individual column, but you can see that you can make like a neon cascade. If you're looking for a particular isotope of neon, you can take columns in parallel, and the outputs from them can be fed to the next column to make further and further enrichments. Those strategies were worked out in detail by the chemical engineers here.
Actually, to have one more comment about Bill Rutherford, he did a whole lot more than that. Basically, he was an expert in anything he set his mind to, and developed not only thermal diffusion columns, but also got into the distillation theory, mass spectrometry. But it's fair to say that most of the people in HH and in private businesses that are working in this now have something to owe Bill Rutherford for their start in life.
Wow.
He developed the program.
Yep, he certainly did.
He came in after the start, but he was the engine that pushed all this.
He really did. Even like Bill Saul was saying, he was the one that knew what the mass spectrum should look like. And we'll see some examples of different masses made up of different things. How do you extract what's the various isotopes out of that? Bill knew. Bill knew. And so I experienced that from him. And there's another one too. We would have a lot of meetings in the nuclear area where Bill would be invited as a source of information for a particular project. And there would be meetings and a lot of people talking and everything like that. And then all of a sudden, Bill would start to talk. The whole room got silent. Because you really wanted to hear what Bill Taylor or Bill Rutherford had to say.
I recall one incident where they were having trouble doing a material balance on tritium, having to do with just accounting for everything and where's all the tritium at in this processing you're doing. Bill figured it out that basically we got molecular sieves in there, and those things are going to act like sponges and then release them. And he just solved the problem, just sitting there listening to this for, a day or two.
That's right. And we went to do actually hydrogen, flooding the same sieves with hydrogen and pushing the tritium out. And we were able to find that was lost.
Everybody was lost until we came up with that answer.
Yep. Okay. Stable isotope enrichment by thermal diffusion. How does it work? Well, basically, convection movement of a gas inside a column that has a cold outer jacket, the blue here, chilled water jacket, and a hot center wire, which could be a wire or a cal rod heater, heated up to 700-800 degrees centigrade. What happens is the hot center would preferentially transport light gas species towards the top, and in the cold water jacket would transport heavy gases. Now they diffusively mix as well as circulate through this, but as they sit there and circulate, eventually you can draw off some gas and see what's the isotopic enrichment of like argon 36, 38, as opposed to the enrichment of argon 40 down at the bottom. So you can also have other columns. You feed the natural abundance in, you can take the product out and further enrich it, and do various strategies like that to achieve the kind of enrichment that you need and want. So the cold water So the design and predictions of this operation were done in-house by Bill Rutherford. Who else? Okay, the monitoring enrichment process, we would analyze the samples by mass spectrometry up until about, not 78 or not?
About 79, yeah.
79, I think. The mass spec at NHH was up so they could run the local samples.
620.
Yeah, and basically it's the same kind of mass spec that we had, other than yours was totally automated. That was good. That was early on. So then the product samples are analyzed independently by us as a separate mass spec group to give what do we find, and you can give your stamp of approval, a normal quality assurance function. Okay, the actual diffusion hardware was actually designed by the chemical engineers at Mound and built by the engineering department from theory and their collected experience. Let's look in detail at what does a real one look like. There's a center nichrome 5 wire that is suspended with a weight at the bottom, and part of that weight, a metal piece, basically the weight is tungsten to have enough mass, and some of the tungsten extends into a pool of mercury. And this plus the wire on top, you can run a current through it and establish the heat that you want and the temperature. And it can be measured by optical pyrometry or other methods for the central wire at visual ports that were about every 4 feet. So you can take these 4 feet blocks of design and you can add as many as you need in order to accomplish the theoretical work you want. So here you can see a number of 4-foot sections assembled on a table. And you can see a little bit closer up to that. But ultimately, in order for gravity to work on this, you have to erect this in a vertical form. And so here you can see that this column is now vertical in an enclosure. Here are some of the people that put it together. This is another interesting thing about management at Mound. This is Dick Valley, who became the head of half of Mound. And the person down below here looking at things is G. Richard Grove, who was one of the early plant manager? Yeah. No? Nuclear director. Okay. Before my time. So, and another person that we know well is, we think this is Ken Foster, which would have been certainly about the same vintage. They all were willing to get their hands involved in the fabrication of something. In fact, they really enjoyed that. Okay, many gaseous stable isotopes were enriched at Mound to high levels. Basically, this shows all the neon and one statement of how much we were able to enrich. Frank has updated some of these. In the early to mid 70s, we were doing about 70% xenon 124, and apparently satisfying customers then. But eventually you want to have it higher than that, and we did achieve 99% for both xenon 124 and 126. Now, they start out as natural abundant xenon of 0.1%. So you got to go through an awful lot of gas to get this up to 99%. So there's other isotopes that can be collected as you do that enrichment. Again, there's an example of a cascade, which was the way to get particular design cuts that you wanted as a product.
One item on the isotope slide for gas thermal diffusion is the original column design of a hot wire was basically used primarily for the really light stuff, like some of the helium separations or trying to concentrate tritium or something. Later on, a design was developed with commercially purchased heater rods that were sheathed in stainless, and we could put those inside of the same kind of a gap column and get into the xenons and kryptons and the higher order things and make those work better.
Neat.
If it wasn't for that, we probably wouldn't have had the success to actually work on the higher isotopes. And in the very end, under Bill Rutherford's guidance, we were making super thin gap thermal diffusion columns for the heavy isotopes and got the xenons up to 99% at the enriched end for 124 and 126. We also worked with Oak Ridge to purchase pre-enriched gas centrifuge cuts that gave us a good head start so we could get that done in a reasonable time frame.
Mm-hmm. Interesting. Thank you. Yes. Okay, going on, thermal diffusion can be used for other gases. For example, in the early years, like the 70s, in that the carbon-13 product from Los Alamos Scientific Laboratory, LASL, as they were known then, came in at about 20%, and yet we wanted to get higher enrichments of that. So that was converted into, from carbon monoxide into methane, and thermal diffusion could be applied to enrich it to like 99%. Similarly with oxygen isotopes, if you look here, you've got 5 different masses. This is mass 32, 33, 34 with both of these, 35 and 36. And Bill Rutherford was able to arrange a column that would actually do those enrichments. And so we saw some pretty unusual mass spectra in our lab as a result of that. But there's a new area that Bill focused on, and that is carbon disulfide to enrich sulfur isotopes. Now, carbon disulfide is a liquid. So we get into the area of liquid thermal diffusion. Liquids have a density that's about 2,000 times the density of 1 atmosphere of gas. So thermal diffusion designs scales to a much thinner gap. How thin, you ask? Well, if you look at this mock-up of some of the original columns, it's 18 inches long, which is really not very long for a thermal diffusion column, and it has a hot center that heats a stainless steel surface, and then there's a cold surface where there's a water jacket that defines the outside temperature. The gap between it is 1/4 of a millimeter, and that's 10,000ths of an inch. So basically the precision needed for a gap required, this is an understatement of today, a careful machining and honing to bore the surfaces smooth, but the real trick is to keep them separated so that they were concentric, so that you have this uniform gap that you can predict the properties of it. And so that was achieved, and there was sulfur enrichment using this. It was also used to enrich chlorine and bromine, is that correct?
Yes.
And then just before he retired, Bill Rutherford and his staff tried to enrich silicon isotopes using liquid thermal diffusion of tetramethylsilane. And so the silane is a single atom in the middle of 4 methyl groups around it. So I think that would be a reason to retire.
these were reasonably slow sellers, although our sulfur inventory was more or less bought out by Argonne National Lab at the very end for some applications. I don't remember anymore, but they basically needed all 30 grams or whatever it was of the stuff, and they got it basically.
Well, as Paul said, I'm a physicist. So for the next few of these, we're going to have a chemist talk about metal isotope enrichment by liquid-liquid chemical exchange and that was done by Bernie Jepson and others. Go ahead, Frank.
Okay. Basically, it is the same phenomena for several isotopes, and we'll start talking about calcium. What the extraction method there was, if you can think of something called a chemical ligand as pictured as a ring or a place that a isotope atom could fit into, think of it as a baseball glove of a certain size. And then certain isotopes fit better in that baseball glove than others. Calcium 40 basically is able, I think, to fit in the baseball glove better and rise in concentration as you go up the column, and therefore the calcium 48 is able to drop in the same fashion along the column. You have stages inside the column where the organic ligand and the liquid aqueous phase pass each other, and they end up enriching and multiplying the effect to the point where you've got something really measurable for calcium in this case and other things in other cases. This was a rather interesting and possibly profitable area of research, although in the end the kind of research they wanted to do with this stuff didn't really pay. So the program, I think, lasted a couple or 3 years, and then that particular part of it died and we got into some other isotopes. The thing to do with this, though, is to keep your liquids clean and to make sure they're well mixed so that the separation can happen at a very high area defined interface. You can go to the next slide.
So these columns is where they would transport, but the collection of the emulsion was down at the bottom.
We would have transport up the column and down the column, and then a way to recycle the streams at each end so that the top organic could be stripped and then sent back into the column as liquid aqueous, and the bottom liquid aqueous could be extracted and sent through the column to rise again, and just multiplying that effect by having the streams in countercurrent recycle was the goal of this. I don't think we ever made any production here, just made measurements at this point, though.
And speaking of the measurements, the ratios of different isotopes of calcium to establish this separation factor per AMU, those analyses were done with the thermal diffusion, the thermal ionization mass spectrometer that Becky Tackett ran for doing isotopes of uranium, plutonium, etc. You can also do calcium. You're right.
Now, one thing later that got quite interesting was that we were going to apply the same technique to uranium enrichment. It was economically competitive compared to the other uranium enrichment processes out there at the time. And what it did was it took the same kind of organic versus aqueous liquid mixing and separating and made 235 fit inside the baseball glove better than the 238, I believe. And over a series of columns, which are pictured in the old Building 51 that we put together, they could have, proven some fairly decent, reactor-grade uranium enrichment for basically power reactors. The program itself, though, had some issues with respect to competition with other ways to do it. The more favored way was laser enrichment of uranium metals, which they finally went with. And all kinds of projections were made, and who was better in terms of the price and so forth was a subject for argument as opposed to reality sometimes. But in the end, we never really did anything with the pilot system we built. There were concerns too about what if you spill something, what if something breaks. We had diked-in areas and so forth, but the funding for the program pretty much went away whenever we got the thing built and improved the principle in some areas. One person that we need to highlight here was Dan Grove in the chemistry, I believe. He found out some interesting chemistry for the uranium III, uranium IV separation that the French were touting as a method that they could sell to a third world country, and they could never make bomb grade uranium out of it. Well, Dan did some research or did some investigation, I don't know how he did it, but he figured out that if you cleaned things up really well and made your uranium extractants very, very pure, that the kinetic limitations that slowed down the enrichment so that supposedly they'd only get to reactor grade for power reactors, those kinetics were speeded up greatly. And this could be something for proliferation. But he did some nice work there. And in a sense, maybe that kind of, sort of did some hurt to the program too, because part of the sales pitch on all this was, this is a method for making reactor grade material and not for making weapons grade material. And that interesting bit of research probably, shot a hole in that theory. So that, but still, it was done.
So note some of the people that worked on this. Certainly Dave Jones is here, and Dick Epley is in the area, I think, but I haven't seen him lately. Bob Tomasowski, right here. Thank you.
Right here, one you're missing. Yeah. Chuck Wade. Yeah.
Chuck, you worked on this also. Very good. Okay. Another chemical separation method here, Frank. We worked on displacement band chromatography to enrich sulfur isotopes.
This was some fairly easy chemistry in terms of using this on a standard chromatographic resin. Indeed, the whole idea of sulfur isotope separation by just chemical means, we tried that in a couple of ways. We had a gas liquid distillation system very early in HH, but the problem was it stuck out the building. We had to just, get rid of that. Somebody else had to work there too. But in the end, this resin band pushing around a band of separated isotopes on a series of chromatographic columns proved the principle that this could be done. And we were going to extend this by bonding a ligand to the resin that could be used for other isotopes, most notably calcium and zinc. Because it would be a cheaper way to do calcium than what we were doing before. But the program, the whole mound, was starting to go down by that time. We did identify a supplier that could do this for us, but I don't know if that work was ever pursued anywhere else or not.
So some of the other products of gas that were sold by Mound were actually separated at Los Alamos using a cryogenic distillation method. Certainly what they would enrich in quantity is carbon-13 and oxygen isotopes using carbon monoxide down a borehole. And like Frank said, they could drill very deep boreholes. Do you know how deep they ever went?
Their biggest columns went down 700 feet in one assembly. All you got to do is move the sand aside and put the thing down. And we couldn't compete with that. So there's always competition between sites for different kinds of work. And Los Alamos had the natural advantage for carbon monoxide distillation and for nitrous oxide distillation to make the nitrogen and the oxygen isotopes at that time. They even figured out how to make it safe compared to some other instances where the NO distillation ended up blowing things things up with certain people.
Right. So Los Alamos was a source of our gas, and they had the advantage of this cryogenic methodology, and they've extended it to a great depth. They also knew how to drill holes 3 feet in diameter and 700 feet deep. They learned how to do that at NTS, I'm sure. Okay, the Stable Isotopes Group contribution added to that work that was done in the nuclear department for DT gas and the RTG work. Again, Bill Rutherford was involved. He made thermal diffusion columns that were used in SW for the normal process tritium enrichment. Later, he made a very high purity tritium diffusion column that was able to generate 99.99 plus % tritium until the helium starts to grow in. But this was used as the high purity tritium portion of a mixture device. As part of the calibration of mass spectrometers, we needed to produce mixtures of deuterium, tritium, and helium III, and whatever protium came along for the ride. So the way we did this was we had 4 separate volumes, and the question was, can we get the ratios of the volumes? Because that's all you really need for doing the mixture composition is the ratios of how much was in this volume compared to this volume of high purity tritium, high purity deuterium, high purity helium III. The way we determined the volumes was the genius of Bill Rutherford. He said, you know that xenon has this unique property that you can cryogenically pump it into a weighing vessel. So you can get like a 300 cc container that you know the tare weight of that. You can put liquid nitrogen around it and suck all the xenon into that bottle and make the pressure of the xenon in the tank literally nothing. Okay, so in doing that, then you can isolate it off, and then you can go and weigh the xenon, knowing what the tare is for that. So each of the volumes of this 4-volume mixture were determined by weighed xenon. He even went to the extreme that there were two containers down at the bottom, side by side, and 2 that were up above, approximately 2 feet higher in the gravitational attraction, so it had a different gravity on it. And so there was an actual difference in pressure from the top to the bottom of the system. That was taken into account in terms of the volume ratios. So ultimately, we were able to put gases into these volumes and make different combinations of mixtures that had a 0.25% accuracy. That's just unheard of any place. Savannah River was able to make deuterium-tritium mixtures with similar kinds of accuracies, but they couldn't add helium. So they basically had day zero mixtures of things. We were able to add various quantities of helium to make that important. Obviously, that made a big impression on me. Okay, Dr. Wilkes was involved with hydrogen isotope cryogenic distillation for the Princeton Plasma Physics Lab, and also working with others that were building cryogenic enrichment facilities for the new T-building tritium complex, working with Mike Embry, and Mike basically designed that. Okay, the last contribution was one we mentioned before, the use of oxygen-16 to avoid neutron emission with the alpha O18 or O17 reaction. The neutrons would have been a problem to limiting the lifetime of spacecraft electronics. Sales, 3 slides. Isotope sales, they changed over the years. From the reports that were issued over a period of 30, 40 years here, I've taken some examples, like fiscal year 1977. The big seller was obviously Helium III. Going to 83, that Helium III sales even increased beyond 77. And by the time we get to 89, we have kind of peaked, and this was rolling off. And we can find out in a minute why that roll-off might have occurred. The other things, there's not necessarily a rhyme or reason to it other than the demand from customers. So who were the customers? Well, there were domestic stable isotopes customers. You can see that the number of those customers dwindled over time, principally because there were starting to be commercial sources of these same isotopes. And then in the foreign case, there were quite a few customers. And these were all in three non-communist areas, and the numbers again went down. But the bottom line is that this is like a $2 to $2.5 million business at the time, which interested people. The increased demand for isotopes and the acquired knowledge of enrichment methods spawned interest in commercializing isotope sales. So actually in 1978, Roger Swind and Vince Avona from the HH group or team established Isotope, basically on Benner Road, just down the street here. It's still there. Isotope was later acquired by different companies and then now is a part of Merck. So it's an ongoing chemical enrichment of isotopes company. Another one is Cambridge Isotopes out of the Cambridge, Massachusetts area. They had long time been a broker for enriched isotopes from various sources in that, but they decided to get into the business. 1987, the Cambridge Isotope Separations Facility was built in Xenia to enrich principally carbon-13 and O18. Cryogenic distillation chosen as the principal enrichment process. As Mound closure became evident, skilled staff from Mound HH that worked there, they became involved over at Xenia. And so Cambridge Isotopes in Xenia now is a major producer of carbon-13 and oxygen-18 and other isotopes. Okay. Go ahead and comment on that, or not.
Well, basically, Isotech and Cambridge have kind of a checkered history in their interactions. I think if Isotech had not tried to restrict the supply that Cambridge would have been able to use, which is an ordinary market competition kind of sale, maybe we never would have built our column out in Xenia. But being entrepreneurs, they have special prices for special customers, and instead of paying that price, we chose to put the money into simply building our own distillation units. And again, we're talking about Bill Rutherford and Bill Roos, who made major contributions to that effort out in Xenia, including going to Los Alamos and basically looking at their designs and hiring some of the Los Alamos folks as consultants. By that time, Los Alamos was shutting down because the government could not compete with a private business. So Los Alamos was able to get maybe 5 kgs a year in their first iteration and 20 kgs a year of carbon-13 in their second iteration. And we took their designs and started at the 20 to 30 level and pushed it on up. And we're a very large supplier of that now. But there's always been some acrimony between Isotech and Cambridge. And it doesn't have to be that way, but that's the way it went. And the original actors are probably long gone too from there, so.
If you're looking for landmarks, the next time you drive on 35 that goes around the south edge of Xenia,
Yeah, the 35 bypass south of Xenia.
you will see this picture, certainly from auto level, but it's these large buildings that are there, and so it's very much an active, ongoing business.
When I came there in 1996, the only piece that was there was, let me see if I get this thing to work here. Right there. Everything else is ruined around it for adding, not back.
And the towers are to be able to lift the cryogenic systems that are around.
Well, the towers are for 018 water distillation.
Oh, okay.
So the 018 systems are above ground. The carbon-13 systems are below ground. The first one I put in with Ruth was that right there. Got about a 60-foot silo over the top, and that column goes down about 480 feet. So we kind of imitated Los Alamos with that one. All his other buildings are different iterations of places to put isotope separation columns. The first isotope separation columns for carbon-13 were down here in these small buildings here. Then we expanded out this way, expanded out that way, put water columns in. The cash flow just kept on coming, we kept on investing. So we're doing quite well now.
Well, after our talk, and this is our last slide, you can have a chance to talk to Frank about this in some detail. But to summarize here, the AEC assignment of stable isotopes enrichment at Mound in 1954 developed and provided enriched isotopes to the free world for nearly 40 years through the sales office at Mound. That's while Mound was functioning. The demand has grown through the development of new tests, medical tests, research applications, and it's been enabled by the availability of highly enriched isotopes. So they kind of feed on each other to increase the demand. So this demand has developed commercial business who provide the isotopes in large enough quantity to make the costs reasonable. The world continues to use the isotope separation technologies that were developed here at Mound through all of our publications and a lot of the people that have gone to the commercial end in the past, and everything is still there in peer-reviewed journals, which is another one of Mound's legacies. So, thank you very much for coming.